Okay, so we're on page 8, and we're going to transition a little bit. Now we're going to start talking about a banked curve. If you look at the bottom of the previous page, a car rounding a curve has two possible sources for the centripetal force. One is friction, that's the tires holding it against the road. The other is gravity, if the curve is banked. And so we're going to look at some questions about a car going around a banked curve. So in this particular curve, it's banked 10 degrees, and we are looking for the coefficient of friction needed for the car to round the curve. Now, the required centripetal force is something that I give you here. The required is 6,000 newtons. So the first thing we're going to do is draw a picture. So here is my banked curve, and here is a race car driving along this banked curve. So we always have a couple of things that happen. We look at a few different vectors. The first one that we always start with is this one. And this one is the force of gravity, otherwise known as the weight. So the force of gravity, we know the mass of the car, and it's actually the same car as on the previous page. And that's where this mass comes from, 1,500 kilograms. Times the acceleration of gravity, which is 10 meters per second squared, means that the weight of this car is 15,000 newtons. So we can write that in here, 15,000. Then we separate these into their component vectors. So we have two component vectors. There is this one, which we call the force perpendicular. This is the force holding it against the surface. And then we have the force parallel. And that is the force that is pulling it down the ramp. So we can make this into a triangle. This would be the force parallel. Let's also put in, this is a 10-degree banked curve, which means this smaller angle is also 10 degrees. So let's find the individual components. So cosine of 10 degrees is the force perpendicular over 15,000, or your minimum step force perpendicular is 15,000 times the cosine of 10 degrees. We find that this force, this perpendicular force, 14,770 newtons. To find the force parallel, we're going to use the sine of 10 degrees. Is the force parallel over 15,000. Your minimum step, 15,000 times the cosine of 10 degrees. And we find that the force pulling this down the ramp is 2,605 newtons. So I'm going to box this off because we're actually looking at a couple of different things in this problem. So here we found its component vectors for the force. So we want to know, what is the coefficient of friction needed for the car to round the curve? And it says that the required centripetal force is 6,000 newtons. Now look, there were two sources on the bottom of page 7. Friction is one source, and it tends to be the major source. And the other source was gravity, if the curve was banked, which it is. So the friction plus the gravity needs to be 6,000 newtons. Or really, it needs to be 6,001. This is the centripetal force. So we're going to come back to that. We are looking for the coefficient of friction in this question. Now the coefficient of friction, the general formula, is the force of friction divided by the normal force. So this right here is the force of friction. And so let's rearrange it for now because we don't know what it is yet. So the force of friction equals the coefficient of friction times the normal force. And the normal force in this question is the force perpendicular, the force that is pushing the two surfaces together. So this is the force of friction. Friction is the coefficient of friction times the normal force. And gravity in this question is not just the Fg. We're looking at the force that is trying to pull it down the curve. And so the gravity here is force parallel. The coefficient of friction times the normal force plus the force perpendicular gives us the centripetal force needed for this question. You could really even erase this and say the force perpendicular. So we have this up here. We're looking at the coefficient of friction times the force perpendicular plus the force parallel needs to be equal to 6,000 newtons. And we're looking for the coefficient of friction. So the reason we did this is because we know what the force perpendicular is. We know what the force parallel is. So we know all of the friction except the coefficient, and we know the source of the gravity. We know the magnitude of the gravity. And so we plug in our numbers, coefficient of friction times force perpendicular, 14,770 newtons, plus the force parallel, which was 2,605 newtons, equals 6,000 newtons. So we'll subtract over the 2,605. Gives us 3,395 newtons. Divide both sides by this. And that gives us a coefficient of friction which is equal to 0.23. So there were two sources that went into the centripetal force here. It was friction and it was the gravity. What if there was no friction? Could we bank this curve enough to where the gravity alone accounted for the centripetal force? So you can do this, and basically, if you have a steeper bank, So let's write this. Without friction, we could make a steeper bank. To make the centripetal force equal 6,000 newtons. It's possible. Let's look into what it's going to take. We need the force parallel to equal the centripetal force, which means that we need this force this force parallel to be 15,000 times the cosine of, really we want to know how steep. So we're looking for theta. Equals, and the required centripetal force is 6,000 newtons. We better check our work here. Look back over here. We had the sine of 10 degrees equals the force parallel over 15,000. And then we wrote cosine. Go back and make sure that yours says sine. And that's going to change it here too. It's a late mistake. 15,000 times the sine of theta equals 6,000 newtons. So a little bit of solving. Sine theta equals 0.4. Finding theta, 23.6 degree bank. So if we banked this curve and this situation 23.6 degrees, we would have no need for friction at all. It could be completely frictionless and still make this turn with this amount of bank.